Well, good evening, everybody. I'm Rick Gering from Naperville Astronomical Association, and this is our Observing Fundamentals program for December 2021. So let me start by wishing everybody a happy solstice today, and let's see what we're going to find out about tonight. It's going to be a little different from usual, from what we usually do as visual astronomers. Since generally, there we go, I hope. You normally as visual astronomers, we're looking at things that are hundreds or thousands or even millions of light years away from us. But tonight we're going to be looking at some things that happen right in our own atmosphere that are close enough that if our cars could go straight up in the air, we could get there on a couple tanks of gas. If we ignore the exosphere, which really doesn't resemble the rest of our atmosphere very much, since it's mostly hydrogen with a few other elements sprinkled in, the part of the atmosphere we're going to be talking about tonight extends only a few hundred miles up from the surface. And really, most of what we're going to be talking about tonight happens within the first 12 or 15 miles. The only thing that happens higher than that are meteors and auroras, which we'll talk about towards the end of tonight's program. But most of the other things we're going to talk about are within a nice long bike ride of the surface of the Earth. So let's see some of the things that are happening there and some of the reasons why they happen. The first reasons that we're going to look at are the scattering of light when it hits things that are in our atmosphere, and the effects of refraction or bending of light when it goes through different medium or different media. We'll start with answering the perennial question of why is the sky blue? Well, the reason is Rayleigh scattering, which is what happens when the sun's rays come flying across space and all of a sudden run into our atmosphere, where they bounce off molecules of air. And when they bounce off the molecules of air, Rayleigh scattering causes the short wavelengths at the blue end of the spectrum to literally bounce all over the sky. It doesn't affect the red and orange wavelengths much at all. Those pretty much come straight through, and the yellow and green sort of in the middle, but they don't bounce around the way the blue and violet light does. And when it gets done bouncing around, we end up with our wonderful blue sky, that little band stretching above the Earth. And in this view from the International Space Station at sunset, you get a sense of just how thin and delicate it is when you compare the thickness of the blue atmosphere to the size of the dark Earth underneath it. It's just a thin blue wall separating us from the very hostile environment that lies just beyond it. And although it's delicate and transparent, it's certainly not insubstantial. We're going to see a little later that it'll cast its own shadow into space, and we're going to see how we can see that and even point it out to our neighbors. If we didn't have an atmosphere, our sky would look like the atmosphere or the sky on the moon, like in the NASA photos. And if you don't believe that that would happen, we can take a photo much closer to the Earth. This was taken at about 70,000 feet. And you can see that without that blue atmosphere, the Earth's sky is also black, even during daylight, if you look at the top of the photograph. Now, in both the photo from the ISS and the photo from 70,000 feet, you notice that there seem almost to be two different parts of our atmosphere. There's a dark blue layer on top and a lighter blue layer below. And we see it here in the 70,000 foot view, and it's even more distinct in the view from the ISS that we have these two bands. And what seems to be going on there is the difference between two different kinds of light scattering. Rayleigh scattering that we already talked about, that shows a preference for scattering the short wavelengths at the blue end of the spectrum. And the other kind of scattering, which is called Mie scattering, named after another physicist, that scatters pretty much all of the wavelengths equally. It doesn't show a preference for any particular wavelengths. It does scatter it mostly forward rather than all around the way Rayleigh scattering does. But what's interesting about the two is that Rayleigh scattering is activated by small particles like molecules of gas, the sort of things that light is likely to strike as it enters the top of our atmosphere, whereas Mie scattering is activated by larger particles, clumps of smoke, dust, water vapor, things that are certainly larger than just molecules of gas. And those are the sort of things that we find deeper in the atmosphere. And that seems to be the explanation for why we have the two different colors of blue in our atmosphere. At the top, we have primarily or almost exclusively Rayleigh scattering, and down underneath we have a mixture of Rayleigh scattering and Mie scattering, which scatters both white light and blue light, plus the fact that there's just more opportunity for scattering to go on as the sunlight enters from above and penetrates the surface. Rayleigh scattering also explains our red sunsets, because at sunset, as you can see in the diagram on the left, if you look at how much atmosphere the light has to come through to reach us when the sun is going down, that's much more atmosphere than when the sun is directly overhead. So there's more opportunity for Rayleigh scattering to occur. More of the blue light is scattered out of the sunlight, and we're left with that gorgeous blue and orange color that we see on a nice sunset on Earth. Now, in addition to scattering, we have another phenomenon called refraction. Refraction is what makes it look like that pen in the bowl of water is bent when we know it's really not. And what causes that? Well, the simplistic explanation is that the speed of light changes depending on the density of the medium that it's passing through. And since that water is denser than the air that the light was passing through right before it hit the water, it goes a little slower in the water than it did in the air. Now, all of the Sheldon Cooper wannabes who are listening out there are, there's steam coming out of their ears right now, because they're saying that no, the speed of light doesn't change. It's just that in a denser medium, it bounces around more because there's more things for it to hit, and it takes longer for it to go through a given distance in a denser medium because it's doing more bouncing around. It's actually going a farther distance, and it seems to be going slower, but it really isn't. That may be correct, but you're also going to get to exactly the same place if you think of the explanation as being that the speed of light changes in a denser medium. So either way is fine with me. There is a nice formula called Snell's law that lets us predict how much the light is going to bend as a result of this, the change in the amount of time it takes the light to cross the medium. And it, in general, depends on the angle of the light when it enters the medium. The steeper the angle when it enters, the steeper the angle of the bend that results from it. So what does this mean for us as visual astronomers? Well, first, it affects where we see the stars. The amount of refraction, as we just said, depends on the angle at which the light is striking the new medium. Sunlight comes in, it strikes our atmosphere, and if it's directly above us, it's striking the atmosphere at essentially a 90-degree angle from our perspective, at least. And there's literally no refraction that results from that. Near the horizon, say down around 5 degrees above the horizon, it's striking the atmosphere at a much bigger angle, and so it bends much more as a result of that. And we get 5.5 minutes of refraction at 10 degrees, almost 10 minutes of refraction at 5 degrees. So as a result, when we look directly above us, the stars are pretty much where we see them. And when we look down near the horizon, the stars seem to be considerably higher in the sky than they really are. The lower C is the actual location of the star near the horizon, but where we see it is where that C up above is, and the same thing then in the middle with the B and B prime locations. The star is not quite where or where we see the star is not exactly where it actually is, but reasonably close. Something interesting happens once we get down below the horizon, and I wanted to call your attention to that on the chart at the left. When we get a half degree below the horizon, we now have 33 minutes and 41 seconds of refraction, which means since a half degree is 30 minutes, and we're refracting upwards 33 minutes, something very neat happens with the sun. When we see the sun right at the horizon, it's actually already below the horizon. And the reason we see it above the horizon is, again, our friend refraction. As we just saw a moment ago, a half degree below the horizon, the sun rises a little over 33 arc minutes, which is a little more than half a degree. But at the horizon itself, refraction is only about 29 arc minutes. And so what happens with the sun is that the bottom gets lifted more than the top, and we end up with a sort of squished or flattened mirage sun sitting above the horizon. And that's what we see rather than the actual sun that is already set. And you have to look closely to see it, but you can see in this picture that that sun definitely does have a flattened or squished quality about it. And that's the result of that differential refraction, with the top not being raised quite as much as the bottom is. That's not the only time that that refraction causes that sort of mirage. Anytime there's a temperature boundary, light bends to the cold side. So what does that mean on a hot summer day when we have relatively or where we have pavements that's even hotter than the air? Well, the air is the cool side. The light from the sky comes down, hits that hot pavement, and refraction causes it to bend to the cold side of the boundary layer, which means it bounces back up. And that's why we look at the hot road ahead of us and we see that blue shimmering light that looks like almost looks like the pavement's wet, or that we're looking over a lake. It's actually the refracted skylight that's bouncing off the hot surface of the road, bending back up into the cool surface of the air and coming to our eyes. The light that bounces off the vehicles and the signs does exactly the same thing. It hits that boundary layer, bounces back up, and we have the reversed or inverted image of the cars and the sign going down seeming to cross the lake, and all from that same phenomenon of light refracting at a temperature boundary layer and bending back to the cold side. When that happens usually over a large body of water, is when this happens in the morning or evening, we get a mirage sun along with the real sun in what's called an Etruscan vase or omega sun mirage. We have the inverted sunrise or the inverted sun below the true sun over the cold water, and that's where again we have the water bending toward, or the light bending towards the cold side, where the where the boundary of the two layers meet at the air-water interface. And why is it called an Etruscan vase or an omega sun? Well, that's an Etruscan vase on the left, and that's the capital Greek letter omega on the right. And if you look at the way the vase comes in and then goes back out, and this letter does the same thing, that's the sort of look that we get where the real sun and the Mirage Sun come together in this illusion. If along with that we add a little bit of scattering, we get a wonderful illusion called the green flash. If you spend a lot of time on cruise ships and looking at sunrises and sunsets over large unobstructed horizons across the water, you'll often get a mirage sun with the real sun, and at the very, very top, the blue light tends to scatter. The red refracts less than the green and the green and yellow, and the green refracts a little bit more, and that causes it to seem to dance above that sinking or rising yellow sun. And if you push the shutter on the camera at exactly the right moment, you might even get a picture of the elusive green flash. Along with the phenomena we've already talked about, some of the things that we see in the atmosphere are caused simply by the fact that where there's light, there's shadows. And the first place that we see light and shadows interplaying with each other is in so-called crepuscular rays, which happens when light and shadow scatters through clouds. Sometimes the clouds are obvious here. There's no mistaking what's causing those shafts of light. Sometimes, however, the sun can be below the horizon, and the clouds can also be below the horizon, and you can see crepuscular rays rising up from the horizon without being able to see the clouds that are causing them. So what are we looking at here? These are actual columns of light that was scattered by me scattering, passes between open spaces between the clouds, and then the clouds themselves account for the dark space between the shafts of light, but those are real three-dimensional scattered columns of light that are coming through and lighting up the surface below. And you can get a sense of that from the shapes of the lit areas on the water down below, where you can see the three-dimensionality and the expansiveness of those shafts of light. They always sort of go back at that angle towards the sun, since that's where they're coming from, but they seem to get narrower as they get closer to the sun, and that's just a perspective effect. It's the same reason that railroad tracks do the same thing when you look off at the distance. So when we see crepuscular rays, that's what we're seeing. The moon can also create crepuscular rays, not nearly as dramatic as the ones that we see from the sun, but a full moon can be bright enough to cause crepuscular rays to come crossing the sky. Now, along with crepuscular rays, we have what are called anti-corpuscular rays. In this particular view, we're looking away from the sun, and if the sun is low enough in the sky near sunrise or sunset, those rays can extend all the way across the sky and end at what's called the anti-solar point, which is the point that is directly opposite the sun on the other side of the planet. And that's what we're seeing here is the anti-corpuscular rays, and again with shadows spaced between them that's caused by the clouds that are creating the rays. Now, besides crepuscular rays, we have another shadow that we can see, and it's in a way much more impressive than the shadows between crepuscular rays, and that's the shadow of the Earth itself. And you can see it here in the picture rising up above the hills in the background. That sort of dark bluish band is the shadow of the Earth being thrown by the setting sun as it sinks behind the horizon that's directly behind us. And then above the shadow of the Earth, we have that pink band that's known as the belt of Venus. So what is that all about? Well, if you think about what's happening at sunset, and if you are the person standing at the X on this diagram, once the sun gets below the horizon, its light goes all over just like it normally would, but part of its light is being blocked by the Earth, and Earth is throwing a shadow that you can see on the right side of that sunlight line that's going up there. Above the shadow, there's sunlight, but what we're seeing there is a backscattering image of the colors of sunset to the left of the diagram, bouncing off the atmosphere to the right and coming back and sort of showing us a reflected image of the sunsets that's happening behind us when we see the belt of Venus in images like this. So if you are in the yard and the neighbors are around and you have a good view of towards the east after sunset, and you can certainly point out that this is their opportunity to see the shadow of the Earth. And they might be impressed, or they might not. There's another time you can see the shadow of the Earth, and most people are impressed by this. If you've never seen the International Space Station cross your sky, you should go to spotthestation.nasa.gov. The address is shown there on the slide. And if you tell them what town you live in and what your email address is, NASA will send you an email whenever the International Space Station is going to be visible crossing your sky, the sky literally from your backyard, and it will tell you where it's going to first appear above the horizon, what direction it'll be going, how high in the sky it will get, and it'll tell you where it's going to disappear and how high it'll be in the sky when it disappears. There are really two kinds of ISS passages. One is where it starts at the horizon, comes up, crosses the sky, and then disappears behind the opposite horizon. And those are certainly impressive because it's always gives you an interesting feeling to look up there and know that there are people up there 250 miles above the Earth traveling 17,500 miles an hour. But the neater ISS passages are the ones that end before it gets to the horizon. Sometimes it'll do exactly what you see in this picture. It will be going along, and all of a sudden it will just disappear. Because what happens then, the reason it just disappeared, is because the ISS flew into the shadow of the Earth. So we have the sun down below the horizon, behind us and to the left. We have the shadow of the Earth going up, as we saw on the last diagram, and the ISS is in the sunlight above the shadow until it reaches that point, and all of a sudden it's gone. And if you have your neighbor watch that happen and then explain to them that what they just saw was the International Space Station flying into the shadow of the Earth, they'll probably be impressed. And if that doesn't impress them, there's one other thing you can try. If you watch very, very carefully, if you have an ISS passage that is going to end above the horizon when the ISS flies into the shadow of the Earth, if you watch just a moment, a split second before it winks out altogether, you'll see its brightness go along steadily, and then it'll drop down for just half a second, less than half a second before it goes away altogether. And what you have just seen when it dropped is when the brightness of the ISS dropped, you've watched the ISS fly into the shadow of Earth's atmosphere. And if that doesn't impress your neighbors, then nothing will. So besides scattering and refraction and shadows and light, we have some other things that happen in the atmosphere when sunlight comes through and meets up with ice crystals and water droplets. And it gives us all kinds of interesting things. The most familiar thing that water and light combine to give us is a rainbow. And what happens to make a rainbow is we have light entering water droplets and bouncing off the inside, in other words, reflecting off the inside surface of the raindrop, then refracting as it exits the raindrop. And as that process happens, it splits the light into a prism of colors. So we get the usual or the familiar rainbow display of red, orange, yellow, green, blue, indigo, and violet. And it forms an arc, invariably 42 degrees in radius. And that arc is the edge of a cone that runs from your eye to the anti-solar point, which is, you remember, is the point exactly opposite from where the sun happens to be at any given moment. And what does that mean? What the most important thing that means is that when you see a rainbow, that is literally your rainbow. No one else sees the same rainbow that you do. If you have someone standing a foot to your left, they're seeing a rainbow that is formed a foot to the left of the one that you're looking at. Because all rainbows are an arc 42 degrees from the line between your eyes and the anti-solar point. And whether it's your eye or the camera that you're using or whatever else that you're using to perceive the rainbow with, it's always going to be different from the one that's seen by anyone near you. Now, since the axis of the rainbow is centered on the anti-solar point, the lower the sun in the sky, the higher the rainbow is going to be, and vice versa. The higher the rainbow is in the sky, the lower the rainbow is going to be. So that means two things. The sun can't be too high in the sky for a rainbow to happen, because if that happened, the rainbow would be a 42-degree arc under the ground and you wouldn't be able to see it. On the other hand, it can't be too low, because if it's well, actually, what does happen if it's too low? Maybe it can be too low. Anyway, when you look at a rainbow, you'll always find red at the top of what we call the primary bow. And we call it the primary bow because it's not at all uncommon to see a secondary bow form up above the primary rainbow. The secondary bow, well, the primary bow is 42 degrees from the line between your eye and the anti-solar point. The secondary bow is always wider, it's 51 degrees, and the space between those two bows is dark. It's called Alexander's dark band, and it happens because light is not refracted into that space. You also notice, however, that whether it's a single rainbow or a double rainbow like this, if you look carefully, the light below the rainbow, or the area below the rainbow, always looks a little bit brighter than the area outside it. And you can see that effect very well in this picture. And that's because the light is refracted inward from the drops that form the bow. And so you get more light under the rainbow, less light on the red side of the rainbow. There's also something called supernumerary arcs that I don't have an illustration of, but they would form underneath the primary rainbow, and they're often fairly delicate and subtle. If you want to be mean to the rainbow, there's an easy way to make it go away. The light from rainbows is vertically polarized because of the angle at which the light is reflected inside the raindrop. If you have a pair of polarized sunglasses, well, the polarized sunglasses are designed to eliminate the horizontally polarized light that comes off horizontal surfaces as glare. But if you turn those polarized sunglasses sideways, well, now instead of being vertically polarized, they're horizontally polarized. And instead of blocking the whole horizontally polarized glare coming off surfaces, they now block the vertically polarized light of the rainbow, and poof, you just made the rainbow disappear. Although why you'd want to make a rainbow disappear is not at all clear to me. There are other things that are similar to rainbows, but not exactly the same thing. And they're caused by different processes, and they come in different sizes. The closest thing to a rainbow, I suppose, is what's called a glory. It's sort of like a full circle rainbow, but it's not caused by the same reflection and refraction that produces a rainbow. It's caused by backscattering of light, usually against clouds or light fog. They're smaller than rainbows, only about 10 or 20 degree radius. And again, since we all see our own glory just the same way we all see our own rainbow, the person seeing it is always smack in the center of the ring. So if you see one from an airplane, which is not uncommon, and you photograph it, you're going to get a nice picture of the airplane in the middle of the glory. And if you are standing on a mountain where you've got a layer of clouds below you, and you have the sun at your back, you're going to be likely to be able to take a picture like the one on the bottom, showing the glory around your head with a shadow that's often a little bit distorted, and it's called a Brocken specter, because there's a place in Germany called Brocken Peak where this is a fairly common phenomenon, where they have clouds below the level where people are hiking or otherwise wandering around. So besides rainbows and glories, we have fog bows, which is, you would like to, as the name suggests, they form when you have fog. They actually do produce prismatic bands, but the prismatic bands in a fog bow are coming from smaller water droplets, which is producing a broader or wider band of color. And the color bands are overlapping and basically canceling each other out. So we end up with either very subtly colored bow or pretty much no color in the fog bow, just a dim red band outside and a blue one inside. They're a little bit, actually about the same size as a rainbow, 35 or 30 to 45 degrees, again centered on the line between your eyes and the anti-solar point. And sometimes there can be glories or rainbows inside them, as you see in the image at the bottom. So we have the white fog bow above, and then the primary and secondary rainbows with the prismatic division of colors below, which makes a pretty nice view. So far, we've been talking about what happens when when light runs into water droplets in the air. Now let's talk about what happens when sunlight mixes with ice crystals. The ice crystals in our atmosphere are almost always going to be symmetrical hexagons, and they'll be either plates, like we see these flat guys here, or columns, which are what you would expect, the taller, longer structures. And when light passes through them, it causes some interesting effects. The most common is a 22-degree ice halo that can form around the sun. It can also form around the moon, but more commonly the sun. And the first thing you notice about them is that they are big. It's a 44-degree diameter, so it covers a pretty big chunk of sky. And they're formed by refraction, again, the bending of the light when the sun or moon is covered by thin cirrus clouds. So we have the light going through the atmosphere, hitting the clouds. The clouds are denser than the surrounding atmosphere. That causes the light to bend. And in the process of bending, we get the division into the prismatic colors, and we have a nice 44-degree ring around the sun. And again, like the space between the two rainbows that we saw earlier, the space inside a 22-degree halo is darker than the space outside because the light is not refracted in that direction. One thing about ice halos, remember that you're looking at the sun, and you do need to take solar precautions. The photographer who took this picture blocked out the sun with that nice big black dot. But it's not even a good idea, honestly, to look at these naked eye without blocking the sun with your thumb or whatever. And certainly never, ever, ever look at one of these in binoculars or a telescope or through a camera lens, because that's a one-way ticket to permanent blindness. Ice halos are sometimes confused with coronas, although that's not what they are. Coronas are completely different. They result from backscattering of light, just like very much like a glory. They result from water droplets, not from ice, again, much like a glory. And they're commonly seen when the full moon or the sun is behind a thin layer of clouds, but that's about their only point in common with the 22-degree halo. They're also smaller, again, about the size of a glory, about 15 degrees in diameter. And it doesn't really, because it's just backscattering. You don't really have a good division into prismatic colors, but you do get some differentiation. So they do look kind of neat. Sun pillars. Sun pillars happen when sunlight hits the flat faces of plate crystals. Again, we're talking about the flat ones, and if they're aligned in the correct manner, they'll produce the reflection will produce a sun pillar. The height of the pillar is going to depend on the degree to which the crystals are tilted, and which way the light, therefore, how high the light goes when it reflects. Since this is a product only of reflection, not of refraction, there's no dividing of the light into the prismatic colors. The sun pillar or moon pillar, or sometimes even Venus pillar, just takes on the color of the object that's creating it, or the object whose light is being reflected. Another common interaction between ice crystals and sunlight produces sundogs, or parhelions, or parhelia, if you want to use the more correct plural form. They generally form, if they're near the horizon, they'll form about 22 degrees to the left and right of the sun. So you can really almost think of them as segments of the ice halo. They become dimmer and wider as the sun gets higher in the sky. They're kind of hard to detect above 40 degrees, and they seldom look as bright as you see in the picture on the right. Usually, sundogs will be visible. I tend to see them primarily against clouds to the left and right of the sun, and they have often a almost pastel quality in the colors. Parhelix circles. I've never seen a parhelix circle, but I would love to. There's sort of the original diamond ring in the sky from what this picture looks like in any event. They form in clouds from sunlight reflecting off ice crystals in the clouds, and unlike most of what we see, they're centered on the zenith, so they're always directly overhead, and they pass through the body of the sun. You'll often see them, I am told, in conjunction with 22-degree halos. As we can see here, we have the prismatic 22-degree halo around the sun. We have the dark area inside the 22-degree halo, as we saw earlier. And then we have the parhelix circle, which does not give us any prismatic division of the colors or division of the light, because it's only a product of reflection, again, like a sun pillar, and does not involve refraction. But it does look pretty neat, I would say. Circumzenithal arcs is another effect of horizontal plate crystals in the atmosphere. Light refracts through them this time instead of reflecting, and they form directly overhead, centered on the zenith. So they're like the parhelix circle in that respect, but they don't create a full circle. They create an arc that can have a radius of anywhere from about 5 degrees to 35 degrees. They tend to have a wider radius when the sun's lower, smaller radius when the sun's higher. You get some nice prismatic division of the colors, and the colors in the circumzenithal arcs tend to be purer than the colors even the colors of a rainbow. Finally, we have circumhorizontal arcs, which are again caused by plate crystals and again caused by refraction, but unlike the circumzenithal arcs that we just saw, these form when there are cirrus clouds to pick them up, and because they're always forming in cirrus clouds, they often have this feathery appearance that we see in the image on the right. And feathers look sort of like flames, and that's apparently where these guys get the nickname fire rainbows, although obviously it's got nothing to do with fire, and since it's refraction through crystals rather than reflection and refraction through water droplets, it's certainly not a rainbow, but they are interesting. They're pretty, and they kind of dress up those clouds a little bit. Final set of lights in the sky that I want to talk about tonight are caused by trespassers from beyond the Earth. There are two things that sort of trespass into our atmosphere as we're going around the sun in our annual trek. One is dust from what is a really remarkably filthy ecliptic, and the other is charged particles from the solar wind. We see dust from the ecliptic primarily in meteor showers. Where does it come from? Well, first, the ecliptic, most of you know, but it's the plane in which Earth goes around the sun, and the other planets are in almost exactly the same plane, give or take a couple of degrees, since the solar system formed out of a spinning flat disk of material that slowly coalesced into the sun and the various planets, and it retained that disk shape after the solar system was born and matured. So that plane that follows the surface of that primordial disk is the ecliptic. As comets go through the inner solar system, we talk about the two tails on comets. One is the gas tail, one is the dust tail. But that dust tail really is a dust tail. It's leaving a trail of material from the comet along its orbital path. And if you don't believe me, you can look at the right side. There's a photograph of Comet Encke that was taken by the Spitzer Space Telescope, and you can see that the comet, both ahead of it and behind it, it's going through a trail of debris that it left behind on earlier passages through the solar system. Major comets can leave major dust. In 1997, Hale-Bopp, for example, was producing 2,000 tons of dust every second when it got near the sun. So it left quite a trail, and other major comets have done the same thing over the millennia. So how does that give us meteor showers? Well, you can see the dirty trail left by the comet as it comes through the solar system. And you can see that in this particular instance, this happens to be a comet whose orbit crosses the orbit of Earth. So every year, literally the same days every year, we will come around and pass through the trail of junk that was left by that comet. And what happens then? Well, first, let's just take a minute, and we have all of the major annual meteor showers that happen every year, and the comets or asteroids in some instances that cause them. You can see in one instance, interestingly, the most famous of all comets, Comet Halley, is the only one that we cross. We cross its orbit twice, once in May, giving us the Eta Aquarid shower, and once in October, giving us the Orionids. So with Halley, we hit both sides of its dust trail. And when we do hit the dust trail of a comet, all those tiny little bits of dust start coming into our atmosphere at really enormous speeds, because don't forget, we're going through space around the sun, plus Earth is spinning on its axis, and that's creating an awful lot of velocity in our atmosphere as it runs into this dust stream. So a typical meteoroid, which is what these guys are called before they hit the atmosphere, weighs 1 or 2 grams. It might be as small as a grain of sand or as big as a green pea. But when it hits our atmosphere, it's accelerated to supersonic speeds, and there's a shock front that forms just ahead of the meteoroid, much like forms when a supersonic aircraft exceeds the speed of sound. And that compressed air gets awfully hot. It heats the surface of the meteoroid to temperatures above 2000 centigrade. And what happens? Well, the little bit of dust or sand or whatever you want to call it literally vaporizes. and leaves a trail of ions behind it that forms the train that we see when a meteor crosses the sky. And the little meteor that keeps crossing in our illustration here gives you a fair idea of how long most meteors last, which is why if you're out looking for meteors, you really need to pay attention, because if you're looking in the wrong direction, you're not going to be able to turn your head in the right direction in time to see them. Unless, of course, it's a little bit bigger meteor, or maybe a little bit brighter one, and it can be classed as a fireball or a bolide. Fireballs are technically only meteors that are brighter than Venus, which means magnitude -4 or brighter. Bolides are less likely to cause an argument about whether they were bright enough, because brightness has nothing to do with it. A bolide is any meteor that explodes. And why would it explode? Well, we have this compressed air right in front of the meteor. There's a vacuum behind it, and that high pressure air pushes itself through little spaces in the structure of the meteor until it emerges into that vacuum. And as it goes through, it literally breaks the meteor apart into even tinier pieces, and we get a nice view like we have here, and sometimes several seconds of persistent train that we can appreciate during a meteor storm, or meteor shower rather. Meteor showers, annual showers, are not the only meteors. There's random stuff out in the ecliptic that we run into every night. The sporadic rate can be anywhere from 4 to 8 meteors an hour, sometimes even more. They tend to be more common in the autumn than in the spring. But like all meteors, we see most of them in the window from midnight to dawn, and that is because of, well, if you think about what's happening when we run into a meteor stream, or just going through our dirty ecliptic, Earth is going from left to right, and it's rotating counterclockwise. So we start at the top right. We have dawn going into daytime. It's going to the right, it's going forward, but its rotation is in the opposite direction, so it kind of slows it down in relative terms. Once you get past noon, we have the front part of the Earth blocking the back of the Earth from seeing any meteors as they cross the sky. And you get the same sort of thing happening from sunset until midnight. Any meteors that you see between sunset and midnight are meteors that are literally going faster through space than we are, and they're catching up with us. So they're not going to be quite as fast, and they're certainly not going to be nearly as many as we see in the space from midnight till dawn, when Earth's rotation is adding to its velocity going through space, and we are the front of Earth is exposed to the meteors that are out there to be had. So that's why for any meteor shower, the prime time is always going to be from midnight till dawn, which is horribly inconvenient, but pretty much unavoidable. There's lots of dust out in the ecliptic, stuff shed from asteroids and comets. A lot of them don't come through often enough to leave a defined annual stream. Other things are left over from collisions that happened back when the solar system was being built. Some people believe that dust storms on Mars can also contribute to the dustiness of the ecliptic, and again, some people think that there's even some interstellar dust out there adding to it. But from whatever source, when the sunlight hits it, you get the same sort of effect that you're seeing here in this old building with the dusty air and the sunlight coming through the windows. So how does that translate to what we can see in our sky? We have dust pretty much throughout the solar system, not as uniform as this diagram suggests. And yes, I am going technically outside our atmosphere for this, but it's so related to what we see otherwise that it really should be covered here. And there's a couple of ways that we see that dusty ecliptic. One is in the zodiacal light, or the so-called false dawn. If you look near the horizon where the sun has set or where the sun is going to come up, and if you're looking at the right time of year, which we'll get to in a moment, you can often see a very subtle triangle of light coming above where the sun crossed the horizon or is about to cross the horizon, extending upwards. It's easy to see in the picture on the left, which is very much overexposed. It's never going to be that bright. It's not even as unsubtle as the picture on the right, although that's closer to reality. It's a very subtle triangle going up from the horizon and extending maybe 30 degrees into the sky. And what you're seeing is the sun reflecting off all of that dust and stuff in our atmosphere, just like the sunlight was reflecting off the shafts of light coming into that old building. And the time of year matters for seeing the zodiacal light because the ecliptic is tilted, which is what gives us summer and winter and spring and fall. And in the northern hemisphere, we tilt towards the sun in summer, away from the sun in winter, and sort of sideways of the sun in spring and fall. So we have noon suns that are high in the sky in summer, because we have a steep ecliptic at noon in the summer. We have very high full moons in winter, and if you haven't noticed that, when we get to full moon this month and next month, and even into February, you can go outside when the moon is full, look up, and I think you're going to be a little bit startled and maybe kind of amazed at how high in the sky the moon can be in winter, because that's when the ecliptic is tilted. It has a high angle to our horizon, is around midnight in wintertime. And in spring and fall, it has that high angle at sunrise and sunset. So we have spring sunset and autumn sunrise. We have the sun making a steep angle with the horizon. Spring sunrise and autumn sunset makes a shallow angle. So if we're looking for the zodiacal light, we want to look at sunset in the spring or sunrise in the autumn, because that's when that triangle is going to be pulled up into the sky and it's going to be most visible. If we look in spring sunrise or autumn sunset, the triangle is going to be very low to the horizon and kind of more horizontal than vertical, and much more difficult to see. The same thing, by the way, affects how easy it is to see Venus and Mercury when they're in the sky, because if you have, for example, when Venus is 40 degrees from the sun, if it's spring at sunset, that 40 degrees may give you 30 degrees above the horizon after the sun goes down. Whereas if it were sunset in autumn, the Venus could still be 40 degrees away from the sun, but only 8 or 10 degrees above the horizon and much more difficult to find. So these are times a year that we want to keep in mind for pretty much anything that we're looking at near the horizon, including the zodiacal light. But the zodiacal light is not limited to the horizon. If you are in a dark enough spot, you can actually trace the zodiacal light all the way across the sky from from west to east, and at the point, the anti-solar point, again, the point in the sky that is directly opposite from where the sun is on the other side of the Earth, there will be a slightly brighter spot called the Gegenschein. It's German for counterglow, and it's, again, sunlight bouncing off all of the collected dust and debris in the plane of the ecliptic. And if you're in a spot that's dark enough to see the Gegenschein, you are indeed in a good dark spot, and I am indeed very jealous. So if you ever see the Gegenschein, you are a lucky astronomer. Dust isn't the only thing that comes traipsing into our atmosphere from beyond. The other and much more, in many ways, much more ominous trespasser is material from the solar wind. And luckily, we have the Van Allen belts that protect us from the solar wind's most direct onslaughts, sort of pushes it up above us and down below us and out around us to protect us from the radiation that it carries. But as the solar wind passes by, it can be brought into our atmosphere through the almost holes, I guess, in the Van Allen belts above the north and south magnetic poles. So we have these energized particles in the solar wind that are pulled into the atmosphere, guided in by our own magnetosphere. And as they come into the atmosphere, the energized particles from the sun run into bits of oxygen and nitrogen and the other things that make up our atmosphere and energize them. And as those molecules, electrons, return to their original state, or the atoms, electrons rather, return to their original state, they re-radiate that energy at specific wavelengths depending on whether you're looking at oxygen or nitrogen or something else. The most common colors that we see as a result of this process are green or red for oxygen. It can also be blue from nitrogen, and there are other possibilities, but very rare. And when that happens, we get the aurora, and the aurora can be a pretty impressive sight if you're in a good spot under the Auroral Oval, which we'll talk about in a minute. And if you're lucky enough to have an auroral display breaking directly overhead, which is not horribly uncommon. Well, the first time I saw that happen, I was about a half heartbeat away from falling on my knees and worshiping it as a god. I can only imagine the reaction that people thousands of years ago who had no idea what these things were must have had when strong auroral displays happened directly above them. It must have been frightening and awesome and wonderful all at once. So where is the Auroral Oval where all these neat things happen? It's a moving target. It's roughly centered on the north and south magnetic poles, but as you can see here, that sometimes it's the poles are not really near the center. This is the version that's put out by the Geophysical Institute at the University of Alaska at Fairbanks. You can get it online. It varies from day to day, and their outer line, the thin line here on the outside, is the expected maximum geographical extent of auroral activity for that for the upcoming period, and then the thicker line are areas where they anticipate that auroras could happen overhead at midnight, which are again much more intense activity layers. Big auroral activity happens in response to major flares and coronal mass ejections from the sun. Those are classed by NASA, and if someone tells you that there was a C-class solar flare, there's nothing to get excited about. That's quite minor. M-class, well, that might be something to talk about. If you're under the auroral oval, it will probably enhance the auroras when it arrives. It takes a couple of days to get from the sun to us. But an X-class flare, and particularly an X-class flare accompanied by a coronal mass ejection, is the kind of thing that can sometimes even bring the aurora far enough south that it can be seen from Chicago. But these are violent and luckily not horribly common events. If you think of the little prominences that we see around the edge of the sun in our hydrogen alpha telescopes, for those of you who have been out to our Solar Saturday events, for example, you've probably seen this. If you think of those little tongues of flame coming off the edge of the sun, under normal circumstances as a polite burp, then an X-class flare with accompanying CME is sort of like projectile vomit, and has the same kinds of potential bad things coming along with it in terms of disruption of radio on Earth that you might expect. But how do you predict whether there are going to be, whether you might have a chance to see the aurora from Chicago or areas like us? Well, there are two things that you would want to look at. One is the BZ index, which measures the strength and direction of the interplanetary magnetic field that's associated with the solar wind. What you are looking for here, you want to see negative numbers for the BZ index, because that indicates a south-directed magnetic field. Again, the Sheldon Cooper wannabes are going to stomp their feet when I say this, because it's not technically accurate. But if you think of a south-directed field as producing attraction between the interplanetary field and Earth's magnetic field, you'll at least get to the right conclusion about which is good for auroras. The second factor that you look at to determine whether an aurora is likely to happen near us is the KP index, which measures geomagnetic activity. NOAA publishes this chart. And if you look on the left-hand side, you'll see that Chicago is at a magnetic latitude of 52.2 degrees. And if you look on the right, the chart on the right, NOAA estimates that for auroral activity to extend as far as we are, to 52.2 degrees, you would need to reach at least a KP index of 7. That might be a little bit overly optimistic, but if you regard it as a minimum, you'll probably be okay. Just don't regard 7 as any kind of a guarantee that there's going to be auroral activity visible from around here. If you don't want to bother checking the BZ index and the KP index, you can get your auroral predictions in pictures. We talked a little bit earlier. We saw the University of Alaska's Geophysical Institute's projection of the Auroral Oval, which you can get from their website, which was on that slide. The NOAA Space Weather Prediction Center publishes its own predictions, which we see here, and you can get those at the addresses shown in blue down at the bottom of the slide, or you can go to spaceweatherlive.com, and they also have a pictorial version of the expected auroral oval for the upcoming day or X number of hours. One final thing that we should address: it's not always dust from the atmosphere or dust from the ecliptic or charged particles from the sun that are trespassing on our atmosphere. Sometimes we do it to ourselves, and we end up with light in our atmosphere that is not the kind of light that we want to see. But we should at least mention them before we finish up. Light pollution has been around for a long time. I don't know why it is, because it doesn't do anyone any good. No one profits from it. And nonetheless, night after night, year after year, decade after decade, we look like what you see on the right if we were being examined by the stars. That's what the stars see when they look at us. And every bit of light that you see on the right side of this slide is light that is going straight up into the sky. It is doing literally no earthly good. I have no idea what it costs to generate the amount of energy needed to produce the light that we see in that picture. But if you multiply it by 365 days a year and 10 years a decade, and God knows how many decades that it's been going on and will be going on, the cost is just astounding. And all it's buying for us is the sky that we see on the left, instead of being able to see the Milky Way. And I do not, for the life of me, understand why we're still doing this. Adding to it now, we have a megalomaniac who wants to put 42,000 satellites into low Earth orbit to make money. And so far, the FCC has approved every request he's made. They've approved over 12,000 of these satellites. SpaceX has announced that they're looking to get it up to at least 42,000. There's a couple thousand of them up there already. And if we allow that to happen, we may very well end up with no more visual astronomy as we've known it in the past at all. So hopefully you will write to your senators and representatives, and something will be done to stop this atrocity from happening. And on that not horribly optimistic note, I've told you what I know about lights of the Earth's atmosphere. So if there's any questions, I'll be happy to try to answer them.
Okay, Rick. At this point, I do not see any questions on either Facebook. Let me double check email. Yeah, I don't see any there either. If anybody wants to chime in, you got a few more minutes before I think we'll call it a night. But very informative, Rick. Thank you. That was great.
Okay, well, in that case, thanks for listening, and see you next time.
All right, thanks a lot, Rick. Yep, bye.